Hello, and this is Gödel's first incompleteness theorem and mathematical truth. So Gödel's first incompleteness theorem is going to tell us that no mathematical system can give a complete account of itself within its own bounds, given that it incorporates some kind of arithmetic. So this is very disturbing to us as mathematicians. Why does the result hold? And really, to me, what does it mean for our concept of truth and abstract objects? So we're going to begin with an overview of mathematics philosophically speaking, basically a crash course if you will. So mathematics we can consider as a community of people who purport to hold knowledge that carries three distinct properties. The first is that it's a priori, the second is that it concerns necessary truths, and the third is that it deals with objects that are called abstract. These objects don't physically instantiate in the world and they don't participate in causal relationships, but they are postulated to exist. So what does this mean for truth then in mathematics? Well, we often consider truth to be the purview of our field. All statements we verify through proof are tautological in nature, and truth seems to be captured in verification, or the production of genuine proof. And this is very much the same as the classic analytic definition of truth in philosophy. But mathematical truth, though, is beyond the mere analytic truth. For example, we can consider shipping containers as helping us understand the iterative conception of sets. So mathematical truth then is going to be, at least for our definition, the conformity of thought to logical laws. So the truth of the statement in mathematics isn't due to the supposition of the laws. The laws already exist. It exists whether we formulate it or not. We use our intuition and the experience of the world to aid us in formulating these laws. So mathematical truth then is a two-natured thing, both of this world and yet not of this world. So now that we understand a little bit about the philosophy of mathematics, we can begin to build up our mathematical content to Gödel's first incompleteness theorem, and this is going to be very definition-y, so strap in. So the first four definitions we're going to look at are going to be these four here. The first is going to be the formalized language, which is any grouping of words or characters that are bound by rules of construction. The second is a primitive term, which is going to be a concept that we can't define from previous terms. The third is going to be the well-formed formulae, a finite sequence of characters contained within the formalized language. And the fourth is a free variable, which is very easily a variable just simply not introduced within the formula it's contained in. So now we can look at the effectively decidable property. We'll consider a property P as effectively decidable if and only if there's going to exist an algorithm for settling within a finite number of steps whether any object is going to contain the property or not. And here we can think of characteristic equations at least. Relatedly as well, the answer to a question is going to be effectively decidable if and only if there's an algorithm which gives us an answer, again in a finite number of steps. However, we're not going to be dealing with the halting problem here, so we could wait till the heat death of the universe. So our next one is going to be the effectively formalized language, L, and L is going to have three characteristics. One, it has a finite number of symbols. Two, syntactic properties like being a term and a whiff and a free variable are effectively decidable, and the syntactic structure is effectively determinable. And three, the syntactic structure, together with the semantic rules, can be used to effectively determine the intended interpretation of any sentence. So now we can finally get to effectively axiomatized formal theories, and we'll call this big T. So big T is going to have an effectively formalized language, where a certain class of those L-whiffs are going to be chosen as axioms. It's effectively decidable what is and is not an axiom, and it's effectively decidable whether any given statement is a correct derivation from the axioms according to the rules. So we can think first-order logic in this. So now the two most important definitions in my mind, at least, are sufficiently strong and negation complete. So a formal theory is sufficiently strong if and only if it's going to capture all effectively decidable numerical properties. And for our big theory T to be negation complete, it's going to have to formally decide every closed whiff contained within the language. So either T is going to be able to produce row or T will produce not row. We're going to note that negation complete is very equivocal to the consistency or the law of bivalence here. So now finally we can get into some arithmetic. And the first one we're going to get into is basic arithmetic, or BA. And this is a formal theory whose language, L, is going to be equipped with the classic logic system of negation and identity, and where each of these 6 schemas are going to be considered an axiom. So We've captured the unique behavior of the natural numbers, at least in terms of multiplication, addition, succession, and zero. And we do have the unique element of zero still in there and everything. The only problem, though, is we seem to lack quantifiers. This, though, actually plays into our favor, as BA can thankfully be shown to be negation complete. But that lack of quantifiers, though, is very problematic. We're losing a lot of linguistic power here, so we might want to look for some stronger theories for arithmetic. So the next one we can move on to is called Robinson arithmetic, or Q, which is BA with quantifiers bounded within the natural numbers. So we're allowed to take on a heck of a lot more linguistic power than BA, and we have the usual first-order logic apparatus, minus, unbounded quantification. We do have a bit of an issue, though. If we take statements within Q, we can show that we cannot prove them within Q, which means that Q is negation complete. Luckily, though, with Q, we do capture something very, very important, and that's called primitive recursive functions. And primitive recursion functions are essentially functions that we can compute. We characterize them by the first three of these rules, and the fourth one is nice in that it says nothing else is a PR function. So what is a PR function? It's something we can compute. It's something that if it's defined from composition of primitive recursive functions, it also is PR. And it's something that if it's defined from PR functions, it is itself PR. So now, as a quick example, we can look at the programmatic language within Python, where we can simply look at defining the factorial. We know the factorial can be manipulated in such a way so as to show that to find the next factorial, we multiply that by its previous factorial. The important bit is just that we define the factorial with the factorial from the previous one here. So now we can finally move into piano arithmetic. Richness at last. So piano arithmetic is going to come equipped with our 6 axioms of Q and 1 induction schema. And this is really good because it comes equipped with our full first-order logic, and we can finally deal with open whiffs in the formalized language. It's just much richer than Q, and so can capture more statements of arithmetic. However, PA can be shown using what's called Godel numbers that it is itself incomplete. If we take Godel's original coding schema, where we take each particular symbol and associate it with a odd number, and then we take each particular free variable and associate that with a even number, we can take the ith plus 1 prime number and then raise it to the power associated with the symbol and multiply all the terms together to get a full whiff, so to say. So for example, s would be equivalent to 2 to the 21, and the statement as well here is equivalent to this gobbledygook of a number. We can further extend this to produce numbers encoding numbers, or what's called super Godel numbers. Now, condensing a lot of material down quickly and taking these 3 assumptions, we can construct a very special whiff called U of y, which essentially, when we observe, this will hold true just when there is not a super Godel number that numbers the proof of the diagonalization of U. But by diagonalizing U itself, we do return the Godel number, even if we have a free variable. So this is our first true Godel statement contained within PA, which brings us right into our first incompleteness theorem. We can think of this semantically and syntactically. Semantically, we're going to be looking at soundness, so proves no falsehoods. Syntactically, which is the stronger, we're going to be looking at consistency, so the law of bivalence must hold here. Now, Godel's first incompleteness theorem has shown us a really fascinating result for mathematical truth. No system containing arithmetic is complete. We can't fully capture the nature of mathematics, nor can we fully capture all the truths in mathematics in a formalized way. Abstract objects, then, are starting to look a little bit more wonky than they originally did. They're definitely the purview of mathematics. This abstract objects enable us to form models and crystallize our mathematical knowledge into concrete ideas. While we may be looking at abstract objects and seeing some fuzziness to them, we might have, hit a quantum conundrum in our field. The abstraction must exist, either on the piece of paper, in our mind, or in reality somewhere. But kind of like virtual particles in space, they exist really to annihilate one another and not exist. As we look closer at the structure of reality and the nature of mathematical truth and knowledge, we are kind of starting to see that abstract objects are not all that smooth after all. They in fact appear a little bit more bubbly, dynamic, and effervescent than we thought. But thank you so much for the presentation, and here are any of the references if you'd like.